Hi guys, welcome to my channel. In this video we are going to solve a questions about the steel structures, and the question will be a member, and this member is subjected to compression force and also flexural forces. So now let's solve the question. But before we solve the question, if you like these videos, if you want to see more of the videos, please subscribe and share with your friends. So now let's solve the question. The first, I'm going to start to calculate as a compression load. Okay, PD. I'm going to make the calculations as a compression member, and then I'm going to calculate the moment capacity of this section at the both axis. So now let's start with the first part as the actual compression member. So it's going to be, let's calculate the slenderness. But for the slenderness, look at here, I'm going to use this table. And my section is suitable for the first case and for the fourth case. This one is for flange, and this one is for web. Okay, so now let's calculate it. For flange, it's going to be B over T equal to 170 over 2 and over thickness of flange, right? 12.7. Look at here, 12.7. And this is equal to 6.7, smaller than 0.56 multiplied the modulus of elasticity over Fy. And Fy is here 355. So 0.56 multiplied 200,000 over 355. And this is equal to 13.3, and you can see that this is smaller than this one, so this is non-cylinder, right? Non-cylinder section. So, and let's do it for the web part. For web part, it's going to be h over thickness of web, and h is going to be calculated 360 minus 2 multiplied the thickness of flange, 12.7 minus 2 multiplied the radius, and over the thickness of web. What is that? 8 millimeter, right? And this is going to be equal to 37.3, and this is smaller than, we're going to check as smaller than 1.49, and multiply the E over Fy, and this is going to be equal to 35.4. Now you can, this is not smaller than, this is not smaller than the 35.4, so this is cylinder, right? Cylinder section. So now we have a member with the cylinder elements, right? So okay, we are going to use this part, the chapter E and the part 7. So we are going to use this part, but before that, let's calculate the slenderness ratio. And due to this slenderness ratio, we are going to decide that QA and QS. So let's do it. If you remember that for non-cylinder, unstiffed element, so flange, sorry, flange, QS is equal to 1. And we are going to also calculate, so we are going to need to calculate QA, but for web part. Okay, so for web, if you remember that it is slender stiffed elements is a web part, so it's going to be H over TW. The formulation is going to be used from here. Look at this one. Cylinder stiffed elements QA. We have to calculate the QA. So it's going to be, if it is smaller than B over T smaller than this value, it's going to be B equal to BE, and we are going to use as the effective area. It's going to be equal to gross cross-sectional area. So the value of the QA is going to be 1. But if it is not, we are going to calculate from here. Okay, so now let's do it. If you remember, h over t was equal to 37.3 149 E over F critical, right? F critical. But F critical, how it's going to be calculated? Let's check. F critical, we are going to make a comparison from this both comparison, you can hear, and then we are going to choose one of them, okay? So let's do it. It's going to be radius of gyration, slenderness ratio. Let's do it for the x and y direction. Radius of gyration. K is 1 multiplied L. What is L? 4,500, right? And this is going to be over the radius of gyration at x, because this is for x and this is 1495. This is going to be 30.1. So radius of gyration for y, it's going to be 1. This is the value of k, 4,500, and over the radius of gyration at y is 37.9, and this is equal to 119, and this is greater than the radius of the slenderness ratio at x, so we are going to use this one. So let's calculate the FE, because I have to calculate the Euler buckling to calculate the F critical, and FE is going to be calculated like that. Pi square multiplied the modulus of elasticity over the the slenderness ratio. Actually, we can write it like that. Okay, and this is going to be, and I have a square here. This is going to be pi square multiplied 200,000 over 119 square. And this is going to be equal to 134.9 megapascal. Now we have an Euler buckling, so let's determine the F critical. So for F critical, we are going to use this slenderness ratio. So this is going to be lambda y is equal to 119. 4.71 multiplied the E over Fy, and this is equal to 1.7, so 4.71 multiplied 200,000 over 355, and this is going to be 11.79. And now you can see this is greater than this one, so we are going to use, let's check which one we are going to use. So this one is greater than this one, we are going to use this formula. So let's use it. Yeah, this is going to be F critical, and this is going to be 0.877 multiplied Fe. So, and this is going to be 0.877 multiplied 134, yeah, 134.9. And this is going to be equal to 122.3 megapascal. Now we got the F critical, but if you remember that I told you we are going to make a comparison here. Look at here, I'm going to show you. We are going to make a comparison due to this one, and we are going to determine QA. Okay, so now let's do it. Here it's going to be H over TW is equal to 37.3, and this is greater than or smaller. We are going to make a check. The value of modulus of elasticity 200,000 over F critical, right? So what is the value of F critical? Look at here. It was this one. So 122.3. And this is going to be 60.25 for this part. And now you can see that this is smaller than this part. This one is smaller than this one. So the B is equal to BE, and the net area, sorry, the effective area of the cross section is equal to gross cross sectional area, and from this we can obtain that QA is equal to effective area over gross cross sectional area, and this is equal to 1. Okay, so now we obtain that one. Q is equal to QS multiplied QA, and this is 1 multiplied 1 is 1. So from this we obtain the Q. So let's write it here. Okay, actually we don't need to write because it is 1. There will be no change. So let's calculate the F critical multiply the area. So we are going to obtain the actual load capacity. Okay, this formulation. We need a coefficient. If you remember, it comes from the LFRD, 0.9 multiplied F critical, 122.3, and multiplied 72, 73, 10 power minus 3, and it's going to be 800.5 kilonewton as the actual load capacity of this section. So now we got the actual load capacity. So let's calculate the moment capacity of the section for the strong axis. So strong axis. Okay. So now we have it. So let's solve it for the strong axis. But I'm going to show you that the tables and which part we are going to use. We are going to use the part F. Okay, chapter F and F2. And so now let's use it. The first we are going to check the compaction. For the flange compaction, I'm going to use this case. Look at here. I'm going to use this case 10 and case 15. Okay, for flange case 10, for web is case 15. So slenderness for flange, and this is going to be B over T is equal to 170 over 2 and over 12.7, and this is 6.7. This is going to be smaller than 0.38, and multiply the modulus of elasticity over Fy, and this is going to be 0.38 multiplied 200,000 over Fy, right? 355. So this is 9. And this section is compact, right? Sorry, the flange. Sorry. Yeah, this flange is compact. So let's do it for, sorry, it's not slenderness. This is compaction. I made a mistake. Compaction. Compactness, actually, you can write it like that. Compactness. So let's calculate the compactness for the web part. So for the web part, it's going to be H over TW, thickness of web, when you call it smaller than 3.76 multiplied the modulus of elasticity over the design strength of steel is used. 3.76 multiplied 200,000 over 355, and this is 89. So this is smaller than this value. Also, the web part is compact. So now we have both parts are compact. So let's calculate the yielding behavior. For yielding behavior, it's going to be MP is equal to elastic modulus section at X, sorry, plastic section modulus of at X multiplied Fy, and 1019 multiplied 10 power 3 and multiplied 355 multiplied 10 power minus 6. So, and this is equal to 361.7 kilonewton meter as the yielding moment. So now I got the yielding moment, but I told you that, so now I have to calculate the lateral torsional buckling. So how we are going to calculate? Look at here. For the lateral torsional buckling, the first I need to calculate LP and LR. Okay, so I'm going to make a comparison LP, LR, and also LB. Okay, LB. So due to this comparison, I'm going to choose one of these. Now you can see here one of these choices, and I'm going to use one of the choices, and due to them, I'm going to obtain the moment. So now let's calculate the LP. Lateral torsional buckling. Okay. So for this one, it's going to be LP 176 multiplied the radius of gyration at y direction and multiplied the E, so modulus of elasticity over Fy. So this is going to be 1.76 multiplied 37.9 and multiplied 200,000 over 355. And this is going to be equal to 1583 millimeter. So now we got the LP. Let's calculate the LR. But before the calculation of LR, I have to calculate the RTS square. Okay. So I need to calculate the RTS. So the inertia at y direction multiply the CV over the elastic section modulus, and this is going to be 10.43 multiplied 10 power 6 and multiplied 313.6 multiplied 10 power 9 over 903.6 multiplied 10 power 3. And due to this, we are going to obtain 2001.5 millimeters square. And from this, RTS is going to be equal to 44.7 millimeter. So now we got the RTS. Let's calculate the LR. Okay, LR. But I don't need to write the formulation of LR. Look at here. The formula is here. I'm just going to apply this formula. This is going to be 1.95 multiplied the 44.7 and multiplied the modulus of elasticity over Fy is going to be equal to 563.4, and I'm going to write it directly here. 563.4 over 0.7. I multiplied. I need to have a J value of J. So J, I'm going to show you what is the value of J at the question. The value of J is here. Look at here, J. 373.2 multiplied 10 power 3 millimeter power 4. So it's going to be like this. Look at here. 373 and 200 multiplied the value of C. So what is C? Let's show you what is C. Look at here. The C is this one. For doubly symmetric I shapes, C is equal to 1. So C is this one. Okay? C is this one. And this is going to be over 903.6 multiplied 10 power 3 and multiplied the H0. So what is H0? H0 is equal to D minus thickness of flange. Okay? So this is D minus thickness of flange, 347.3. And this is going to be 37322 multiplied 1 over 903.6 multiplied the 10 power 3 and multiplied 347.3. 676 multiplied 0.7 over, if you remember the ratio of modulus of elasticity over Fy, that was 563.4, and now it's going to be the down, and the formula is this one. So due to this, Lr, it's going to be equal to 4,774 millimeter. And if you remember that we calculate the Lp, it is also equal to 1583 millimeter, and we have an Lb 4,500 millimeter. So now let's make a comparison. Lp smaller than Lb and smaller than Lr. Okay, so which the formula of the moment is going to be used? So this one, right? We are going to use this one. Mn equal to Cb and Mp and blah blah blah. So now look at here. To calculation of this formula, we need to calculate Cb. Okay, the ratio of the moments. So how it's going to be calculated from here? So now it's going to be calculated like that. For example, this is our beam, and we have a span as L, but we try to determine the moment at X, and we have forces here as a distributed load, as W, okay? But look at here, at strong axis, I'm gonna show you in the question. At strong axis, mdx equal to 100 kilonewton meter. Okay, so now I have to determine the forces. So the force at mdx. Okay, so what force created that moment? So now let's determine it. It's going to be determined like that. For example, this one, it's going to be 100, the moment at x axis, okay, equal to q multiplied the L square over 8, right? From here, if you remember that L is 4.5 meter, and the Q, it's going to be calculated as 39.5. So now, how to determine the moment at X distance? It's going to be moment at X equal to W multiplied L multiplied X over 2 minus W multiplied X squared over 2. The formula is this one. So now, for example, this is the moment diagram. For example, this is the moment diagram, and this is the midpoint of beam. Okay, this is the 1 quarter, and this is the 3rd quarter. So this is going to be 1,125, 2,250, and 3,75. Yes, as the distance. Okay, this is 0, and this is 4,500. So now let's write this distance into this equation, and we are going to obtain the moment value. So now I did it for you, but you are going to try it, I guess, before the exams, or because if you try by yourself, you are going to understand better. And this is 75. Okay, so let's calculate the CB. Now we got the moments. For CB, if you remember the formula, 12.5 is a moment at maximum. 2.5 multiplied the maximum moment, and 3 multiplied MA plus 4 multiplied MB plus 3 multiplied MC. And from here, 12.5 multiplied 100, right? Because the maximum moment is here 100. So over 12.5 multiplied 100 plus 3 multiplied 75 plus 4 multiplied 100 and plus 3 multiplied 75. So from here, I'm going to obtain as the ratio equal to 1.14. Okay, so now we got the ratio of the moment as 1.14. So now let's delete here. So now I got the value of CB. Let's calculate the moment. I got this page to here. Okay, so now let's do it. I got the CB. If I got the CB, now I can calculate the moment. So the formulation of moment, let's show you that what is the formula of the moment. The formula of moment is this one. If you remember that, we are going to use this formula. And the moment N is equal to CB multiplied MP minus 0.7 multiplied the Fy and multiply the elastic section modulus at X and multiply the LB minus LP over LR minus LP. And we are going to multiply this. So it's going to be smaller than MP. Okay. So now let's calculate this formula. It's going to be 1.14, the value of CB, if you remember, we calculated. And it's going to be MP, if you remember that at the first when I calculate and the moment yielding, okay, this one. So this is the yielding. And 1.14 multiplied 361.7 and multiply 10 power 6 minus 361 multiply 10 power 6 and minus 0.7 multiplied 355 multiplied the elastic section modulus and multiplied the 4.5. Look at here, and this all in the meter, so I'm going to write it here also in the meter. Okay, units has to be units have to be the same. If you want to get a correct answer, you have to write in the exact units for all. So this is going to be 4.774 minus 1.583. And from here, I'm going to obtain 269.3 kilonewton meter. And this is, if you remember, that smaller than MP is equal to 361.7 kilonewton meter. And so now let's calculate the moment capacity. For the moment capacity, I have to multiply with the coefficient. So it's going to be 0.9 multiplied 269.3. And this is going to be equal to 242.4 kilonewton meter as the moment capacity of the strong axis. So now let's do it for the weak axis, and it's going to be a short one. And we are going to calculate the yielding behavior. So it's going to be yielding, and MP is equal to Fy multiplied the plastic section modulus at Y, and this is going to be 355 multiply 10 power 3 and multiply 191.1 multiplied 10 power minus 6. And this is going to be equal to 67.8 kilonewton meter. And now we got the yielding moment. So let's calculate for the local buckling, because here there is no torsional buckling. But we don't need to calculate also for the local buckling because compact flange. Okay, it has a compact flange, so we don't need to calculate also local buckling. So it's going to be for B. I can write that no need local buckling. Okay, and this is going to be the coefficient of LFRD equal to 0.9 multiplied 67.8, and this is going to be 61 kilonewton meter as the capacity of weak axis. So now we got the also capacity full capacity of weak axis. So now we can make a check for the safety. Check the safety. And for the checking the safety, it's going to be PR over PC. The forces is applied at first, that was 170 kilonewton, over the actual force capacity of this section is 800.5 kilonewton. Okay, and this is going to be 0.21 and it's greater than 0.2. So for this check is okay. So let's do the total check. It's going to be PR over PC plus 8 over 9 multiplied the moment MRX, okay, MRX over MCX plus and a moment at y direction over the moment capacity of this member at y direction. The formula is this one. That should be smaller than 1. If it is smaller than 1, it is safe. If it is not, it is not safe. So let's write it. 170 over 800.5 plus 8 over 9 multiplied 100 over 242.4 and plus 20 over 61. This is smaller than, sorry, this is equal to, actually we have to calculate. And this is equal to 0.87. And this is smaller than 1. So we can say that the section is safe. So now you can see that the question is solved. If you like these videos, if you want to see more of the videos, please subscribe and share with your friends. See you on the next question.